All right. So the recorder is on. I'm recording to the cloud. And it is time to get started. Okay, excellent. All right. So just for, I guess, entertainment purposes, let me give you guys a problem to solve. Okay. So let's just say that one person has six regular dices. Okay. So basically six-faced dices. Each one can go from one to six. Okay, that's one person. Person A, we'll call that person A. Person B has nine four-faced dices. So each dice can only go from one to four. All right. I want to calculate the chances, the probability that the person with the nine four-faced dices would end up with a sum of the four numbers, the four dices, that is higher than the person that has the six-faced dices. And you can use a program to do it. Don't even bother to try to look for a nice, elegant, closed mathematical form. So the question is, how would you do that? Okay, first of all, do you understand the question? Okay, all right, so let me write it because some people are better, including myself, when you can read the question itself. So I'm gonna start mouse pad. Okay, there we go. So we'll say person A has six-faced dices, and then person B has nine four-faced dices. Okay, and then so obviously, with six-faced dices, you throw the dices, and then you add up the numbers from each dice to a sum. And then with the nine four-faced dices, you do the same thing. So the question is, what is the probability that person B has a sum of all the dices to be greater than the sum of all the dices of person A? Okay, how would you solve that problem? You are allowed to write programs to do it, so you can rely on code on the computer to do it. So I'll let you guys, yeah, go ahead. So you do need to know all the possible something, but it's not about, it's not about the power set. Okay, this has nothing to do with the power set. So if when you look at the four-faced dices, okay, I'll give you an example, right? So you can end up with this. Okay, that's the smallest number, with the four-faced dice. This would be another one, and this would be another one, and so on. So with the four-faced dices, you end up with six to the power of six, possible configurations. Because the first dice has six numbers, the second dice has six numbers, the third dice also has six numbers. So the total number of ways to have the values on the dices would be six times six times six times six times six times six. In other words, six to the power of six. Is that okay? And for the nine-faced dices, it's going to be, one, 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 one is one configuration, and then you just basically go, blah, blah, blah. Yep, go ahead. So when the six dices are all sixes, and then the four dices are all fours, then they all add up to 36. So the one does not win the other one. So you have to, yeah, go ahead. It's a There is a double loop eventually, but that's not where you start. So I can show you the solution. I was asked about this question because somebody who is currently taking 440 from Sac City was given this particular problem to solve. And for whatever strange reason, that person came to me and asked that question. So this is my super quick and dirty program to do it. So you basically maintain an array of the sums, and each item in sum 4 is basically the frequency. Okay, each element is representing the frequency of a particular sum occurring. Okay, and then same thing for the 6-phase dices. So I have 2 arrays, and then I have just a bunch of. I did not bother to implement this recursively. And these 2 are not needed anymore because I probably misunderstood what memset does, and it's not doing what I needed to do, which is to initialize both of those arrays. So this really ugly piece of code here, yes, I admit this is really super ugly piece of code, is to go through the 6-phase dices. Okay, the first dice, second dice, third dice, fourth dice, and the fifth and the sixth dice. Each one will go from 1 to 6, and this is nested. Okay, I did not bother to indent everything correctly. So if I were to indent everything, it would look like this. Yes, it is some ugly piece of code, okay? But the most important part here is sum 6, okay, with a square bracket. It is the sum of I1 all the way to I6. It's incrementing by 1. In other words, I have just observed, okay, another case where the sum of the 6 dices add up to whatever this number turns out to be. Okay, so that means this loop here from line 16 to line 22 is going to process all the possible cases with the 6-phased dices, and it ends up counting in each sum what is the frequency of that particular sum occurring. Is that okay? Yes. Nope, it's not easy because okay, so if you think about 17, okay, how many ways can you end up with 17 when you have 6-phased dices? How many ways? Well, you can have a 6 on the first one, a 6 on the second one, a 2 on the third one, and then one's did I miscalculate? 6 plus 6 is 12, 14, 15, 16, 17. Oh, that is correct. That's one way to add up to 17. What is another way to add up to 17? Now remember, within each one, okay, this is one way. This is dice number 1, but you can also have 6, 2, 6, 1, 1, 1 to add up to 17, right? You can have 6, 2, 1, 1, 1, 6 to add up to 17. So this way, to try to look at it is really difficult. Yes. But you cannot just look at each number because you have to look at the sum. Okay, I'll let you implement your program your way, and I'll see you next week to find out how that goes. Okay, so this is my way of processing it. Okay, and then this is the second loop, which is even uglier because it has 9 nested level of a for loop, but the same principle. Okay, because the second loop or the second uh, ugly loop is starting from line 23, ending on line 32. It is just simulating, the 9 4-phased dice, all the possible cases. And once again, I'm adding up the values of every single dice and say the frequency of that sum is just increased by 1. I just observed another instance of that particular sum. Okay, so then to do the actual calculation, I say for every case from um, sum sum 6. Okay, for every case of sum 6, I'm adding up all the frequencies of sum 4 where they can add up. I'm adding up the frequencies of all the sums of the faced dice cases that add up to more than the specific case, which is controlled by I1 of the six faced dices. So then I do the multiplication and some addition, and the whole thing is basically calculated this way. So you guys may be thinking, but Tech, are we going to have to deal with something like this? And what made me, mention this particular problem? It's because of the Sac City student who came to me and asked about this question. At first, it stumped me because at first, I thought I had to solve it mathematically with a closed form. So I was thinking like, wow, but there are a lot of special cases here, and it's pretty hard to come up with a closed form. And then I asked the student, can we use a program to do it? And then the student said, yeah, we're supposed to use a program to do it. And then right at that moment, I go like, oh, okay, that makes it super easy because then I can just kind of do it this way. And the according to my program, and you guys are encouraged to do something like this, ignore the first two number. I think the chances is 57% of a chance. So 50% of a chance the person who has the 9 4-faced dices would add up to a value that is greater than the person who has the six faced dices. But you guys are welcome to kind of come up with your own algorithm and kind of see if you can come up with something that's much more elegant than my approach. But then I was in a time crunch, I only got like 20 minutes to do it. All right. Yep. Well, I it's now that's really a good question, but it's also a very difficult question to answer, um, because in my mind, I say, okay, so I have to calculate all the probability, or I have to look up all the ways, number of ways to add up to 17. Then I have to look up all the ways to add up to 18, 19, 20, all the way to 36 with the other case, because that's what I need to do. So to come up with this number, the frequency, of or the number of ways a six faced dices cannot add up to 17 was not an easy problem. But to use a program, it's easy to brute force the whole thing. The instructor was also putting a constraint on the whole thing. The algorithm has to be done within a minute on a reasonable platform. Okay, so now you look at this and go like, but Tech, this is a really brute force approach. Is it going to finish in a minute? Well, okay, so you have to look at the order of magnitude. 6 to the power of 6 is it's less than 50,000, okay? And then 4 to the power of 9 is about 200 and something thousand, okay? So even if you have to multiply those two, which we don't, okay, you're still looking at a reasonable number that modern day computers have no problem dealing with, okay? So if I were to look at how much time this algorithm or this implementation on this computer takes, I can just do a time count. It took 2 milliseconds in real time, and of which 2 milliseconds are used by the system. So the program itself consumed basically a negligible, non-measurable amount of time in milliseconds. It was that fast. So, but what you asked was really the question to ask is, how did I come up with this? So I just think of, okay, if I have to calculate the chances, then I have to know at least how many ways can the six-faced dices add up to 17. Then I also have to compute the number of ways for the other person, the one with 9 4-faced dices, to add up to 19, 18, 19, 20, and so on. And and then I look at the whole thing and go like, okay, there's no easy way to find a closed form to use your combination, permutation, which we haven't talked about here in this class yet. But since I was able to use a brute force approach, and the number of iterations of the brute force approach does not look bad at all. Okay, 200 and something thousand iterations, and each iteration just has to increment one value out of an array that has 37 items. It's not a problem. Right. So this I1 here is is basically the sum from the six phase sizes. And somebody's going to complain and go like that tech, there's no way they can add up to zero because the smallest number is six. It's okay, I'm lazy and I'm just going for zero because the frequency of the six phase dices adding up to zero is simply zero. It doesn't contribute to anything. Okay, but is it wrong to do it? No, it's not wrong. I just wasted a little bit of computational cycle. No big problem here, right? And then the inner loop is going from I1 plus one. So I1 is um, the sum of the six phase dices. I2 is the sum of the nine four phased dices. But that has to start with I1 plus one because we are looking for the probability where the person with the nine four phase dices has a sum that is greater than the person who has the six phase dices. So that means this is the correct nesting. And then the nested loop just has to add up, oh, the frequency of 18, 19, 20, just add up everything. So that's just sum plus equal to sum 4. And then the actual frequency corresponding to a specific number from the six phase dices, and then all the cases of the uh, four phase dices is going to be the multiplication or the product between the frequency of the six phase dices and the combined frequency of the four phase dices. So that's kind of how the whole thing is done. And then the final calculation is to um, divide that combined frequency thing by 6 to the power of 6 times 4 to the power of 9, which basically is the number of every single possible cross cases. Okay, every single case of the six phase dices and every single case of the four phase dices. So, yep. I will let you implement your program and then we can take a look at it on next Monday. Because we are not going to use the time to talk about the potential implementation. That is, by the way, one of the main differences between someone with the personality type of an INTP versus somebody who has a personality of ENTP. If you guys are into the MBTI thing, how many people did the test? Some of you, okay. So as an INTP, I need to think on my own. I cannot be working on a problem while listening to somebody else, trying, to talk to themselves, about the solution, because I need to hear my own voices. And then ENTPs, on the other hand, like to bounce ideas off of other people. So as you can probably imagine, at the workplace, ENTPs and INTPs, they have similar, features, but it's difficult to work together. The best combo, by the way, if you're at work as a software engineer or anything that is technical, the most potent combination is an INTP with an INTJ. That is one of the most potent combination. But since this is not a class in psychology, I cannot go any further into that. That was a hand earlier. Yes. So it'll be the O and then 6 to the power of 6, maximum of 6 to the power of 6, and uh, or you can just add those two. That's basically the time complexity. Yep. So the actual time complexity is going to be 6 to the power of 6 plus, in this case, 4 to the power of 9, which sounds really bad, but it's really not too bad in this case. All right, cool. So now we are moving on to the next topic, which is about relations. I thought we were moving on to propositional logic, which is really kind of a fun, interesting topic. But before that, we have to get to relations first. So we'll talk about relations as a topic. All right. All right. So the first thing I need to clarify is what I mean by, what is a relation? Okay. A relation that we are all familiar with is less than or equal to or greater than. Those are relations. In other words, in the set of integers, okay, we'll just use it as an example. In the set of integers, that is a relation that relates certain numbers. Okay. So let me kind of go into the nitty-gritty detail first, and then we'll back up and talk about examples. So a relation technically is whether two elements of a set are related or not in a particular way. Of course, this does not really say much, okay, which is kind of the theme of this class. So we'll consider a relation R that is defined over a set X. The first thing is R has to be a subset of the Cartesian product of X with itself, okay? Now, I know this reminds you of functions, but relations have nothing to do with functions, okay? They are two almost entirely different things. They're not entirely different, but from our perspective, at least at this point, we'll consider those two things as entirely different, okay? So using this notation, okay, I can also do something like this. Okay, I'm going to use the mouse pad here to denote. Okay, so I can use less than or equal to as the name of a set. Okay, I know that is awfully strange as the name of a set, but it is just a symbol. Okay. And now I can say this is a subset of, okay, and it's going to be, since we talked about integers, so it's going to be the Cartesian product of integers and integers. So we are looking at a really odd subset that is called less than or equal to, and it is a subset of the Cartesian product of integers and integers. Okay. Now, because it is a set, so we are interested in what's in the set. Okay. So now I can say, what members are in that particular set. Okay. Well, what does each member look like in this particular set? In other words, if I look at the Cartesian product between integers and integers, can someone give me an example of an element of just the Cartesian product between integers and integers? Just one example. Yes. -7, comma 2 as a two tuple, 0, 0 as a two tuple, 4, 7 as a two tuple, blah, 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 and so on. Okay. So in this case, I'm particularly interested in what is in the subset of less than or equal to. Okay. So 5, comma 6 is an element of less than or equal to as a set. -2, -1, and 0 is an element of less than or equal to. I mean, you guys are probably getting the idea. Okay, 5 and say 100 is an element of less than or equal to, and so on. Okay, so let me just kind of pause here. Are you understanding what I mean when we look at less than or equal to as a relation, but it is also seen as a subset of the Cartesian product of Z, Cartesian product with Z. We're only keeping the two tuples in the subset where the first item is actually less than or equal to the second item. Are we good so far? All right. And that's basically what the relation is using this particular definition. So let me see if there are any questions about this example of a general relation that we need to talk about. So, okay, 105 is not an element of the set that has a really strange name of less than or equal to. Is that okay? So we are looking at something that you are really familiar with, which are comparison operators, but we are now looking at the comparison operator as a subset of the Cartesian product of the things that are being compared. Are we good so far? Okay. So you look at this and go like, so it's not even worth the time to talk about because we all understand what is less than or equal to. Or do we? Okay. And what is so important about less than or equal to? Well, how is less than or equal to important? So I'll give you an example and you guys can tell me what you think of it. So let's just say that you cannot really get any other job other than, being a game developer. I'm so sorry, but now you're a game developer. And you are tasked with writing an algorithm to publish quote unquote gamer of the week for this particular game company. Okay, are we good so far? I hope you guys play enough games to kind of understand what this is about. Okay, so how do you determine who is quote unquote the gamer of the week? Well, there are many things you can use to determine that, right? Because after all, the whole idea is to encourage people to play that video game, to spend money in the video game, and to get their friends into this game as much as possible. So now you go like, I can see that how much money they spend on champion skins is going to be one of the factors because we want people just to waste their money on something that is completely non-functional. Okay, okay, fine. Okay, that's one of the factors. Two, how many new people do they get into this game? Are they introducing new people into this game? Because we want to get more people hooked into this game. So now you look at, okay, how many people did they bring into this game? Now, obviously, that can be spoofed by people just registering with different IDs and just keep coming, right? Three, um, we want to see how much time this person spends in the game because the more time they spend in the game, the more likely their friends would also spend their time in the game with this person. So now we look at that as another factor. Okay, so there's a bazillion number of things that you want to consider as okay, how do we want to calculate, or how do we want to determine, who is quote unquote uh, a more contributing gamer than the rest. Okay, is that okay? So now you guys are all, you're all familiar with C++ object-oriented programming because that's how you can get into 430, which you must be in or have taken already. So you go like, oh, I can just overload the less than or equal to symbol to see who is lesser of a gamer or not as good of a gamer as the other person. Okay, and then you take into so every gamer is now an object with all of these bazillion attributes, and then you have your super duper algorithm to perform the comparison. Okay, so are we good so far? All right. So now you have a list of all the gamers, okay, that is on the system. And you go like, oh, great. I just need to sort this particular array using the less than or equal to operator that I have just overloaded, and we are done. Okay, I don't even have to implement my own sorting algorithm because C++ and C already has quick sort implemented in either the template library or the C library. Are we good so far? Only to find out that your algorithm does not work. Okay. And the reason why your algorithm does not work is you did not check to make sure that the way you define less than or equal to when it comes to gamers is totally ordered. So now we have to get into the concept of what is totally ordered. If there's something called totally ordered, there has to be something that is called partially ordered. Then and you'll be correct. So I'm reversing the way I introduce these concepts, this semester just a little bit, just to kind of kick things up, move things around a little bit so it's more interesting. So I'm going to direct you to YouTube because there's a really interesting beer commercial that helps to illustrate all of these concepts. So there's a beer commercial that focuses on rich but not smooth. Okay. This is a good one. I think that's the one that I want to, look at. And we'll turn on the, oh, my Bluetooth is connected. Okay. So I think you guys got the gist of what this commercial is about. Okay. So I'm gonna make sure that we understand. Okay. So I'm just gonna say out loud. Okay. So what they are trying to say is one of the, I mean, obviously this is very gender biased. So one of the men was smooth but not rich. The other one was rich but not smooth. And the beer itself is rich and smooth. So I think the implied message is it's better to be rich and smooth rather than just being rich or just smooth without the other. Okay. And then there's tack. And then there's tack being not rich and also not smooth. So now you have to think about the ordering of these things because everything is about ordering. So now you go like, okay, so let's have a ranking system here and rank the 4 possible situations. Okay, so now we go to mousepad here, and then we go like, we say rich and smooth is at least as good as the following, which is rich and not smooth. And then we have not rich and smooth. And then finally we have tack, which is not smooth. Oh, I misspelled rich, and that's why I'm not rich. Okay, not rich and not smooth. There we go. Okay, is that okay? So does everybody get the implied message from the commercial? Being rich and smooth is the best. Okay. So now we look at this and go like, okay, what about rich and not smooth? So now we look at rich and not smooth. Okay, is at least as good as. Oh, I missed one thing that is really important because it is also itself. So rich and smooth is also supposed to be here. In other words, a beer that is rich and smooth is at least as good as another beer that is also rich and smooth. So I have to remember that rich and smooth is at least as good as itself. Okay. So now we go to the next one, okay, which is rich and not smooth is at least as good as rich and not smooth itself. But the only thing left that I can say is tack, because there's no implication whatsoever, at least not from the beer commercial, of how rich and not smooth compared to not rich and smooth. Is that okay? All right. So now we go to yet another case, which is not rich and smooth is at least as good as, okay, itself, okay, not rich and smooth. And again, tack. Is that okay? And now we have tack left. Tack is at least as good as, unfortunately, in this case, just myself. Okay? Now, the important part about this beer commercial is it is not totally ordered. How is it not totally ordered? Because I cannot say between rich and not smooth and not rich and smooth which one is at least as good as the other one. Is that okay? So without that relation between these two elements defined, this particular ordering is called partially ordered. It is not totally ordered, it is only partially ordered. So if you define your less than or equal to operator without considering whether the way you define it is supposed to be supposed to be totally ordered or only partially ordered, anything that is partially ordered cannot be sorted. You cannot say this is the best because not everything can be related to make that determination of is this better than that. Is that okay? All right. That is the importance of the topic of relation, because we know the relation less than or equal to with respect to numbers, numerical values. Okay, not a problem. But when you are asked to sort an array of something that is not just a single number, and you have the flexibility to redefine what is less than or equal to, and you need to sort the array, you have to make sure that the way you define the operator less than or equal to has to be totally ordered. So are we good so far with this topic? Are we understanding the importance of this topic? Okay. So now we can start to introduce the properties of a relation. Okay, so we'll use, this is a concrete example, but we can skip that because we talked about the example of integers already. So the way we define a relation can be relatively random. Okay, so this is a really random case. So X is a set with only 4 elements, A, B, C, and D. And the relation R is really just a subset of the Cartesian product between X and itself. Are we convinced that this R here, as it is defined, is a subset of the Cartesian product between X and itself? Okay, that's fairly obvious. Okay, so in this case, okay, if R is defined this way, we have several notations that we can use. We can say that A, R, B is true. In other words, we can put the name of the relation between the two elements that we need to question. Are those two elements related by R? So ARB is asking, does A as an element of X relate to B as an element of X? If you can find AB as a two-tuple in R as a set, then yes, ARB is true. Is that okay? It's just a notation. It is the presence of AB as a two-tuple. What about BC is an element of R? Well, that is true. Okay, BC as a two-tuple really is an element of R here. So BC is an element of R is another way to say BRC. So those two are just different notations to mean exactly the same thing. Element blah relates to element blah blah. Okay, is it true or not? Do we have any questions about the notations? Okay, and then I have two examples where the answer is false. So B does not relate to itself because I don't see BB as an element in R. So BRB as an expression is false because it is asking, does B relate to itself using R as a relation? The answer is no or false, it does not. And then DC as an element of R is also false because we definitely do not see DC as a two-tuple in the definition of R as a set. So are we doing okay so far in terms of the notations? I can switch between the set notation or use the relation notation, just as a shorthand. Are we good so far? All right. Okay. So now we look at properties of relations. This is also where when we introduce quantified expressions, which I know all of you really like, not really, right? But it is important, okay? It is a language that you have to learn because in computer science, we do use these notations a lot. So we talk about reflexive first, okay? A relation is said to be reflexive, or I should say a relation R over a set X is reflexive if and only if this is true. For every element in set X, EE as a two-tuple exists in R. Okay, so now we'll take a look at some examples. And to do the examples, I'll try another tool today, okay, instead of using the tablet. Joplin, there we go. I don't think I have used Joplin in this class, have I? I have, okay. So you guys know Joplin already. Oh yeah, I remember now. Okay, so this is Joplin, okay. And I'll start here. Okay, so I'll give you an example and you guys have to tell me whether R is reflexive or not. So the first thing I need to do is to define what is in set X. And, I think I will make a new note here. So give me a second. And so let me make a new note based on today's date. All right, today is 2025-0305. There we go. All right, so I'm going to define x first. Okay, so with the following example, x is defined to be have A, B, C as elements. Okay, and then I have to define R. Okay, so under this, the first one is what if R is defined to be an empty set? So the question is the empty set R reflexive? The answer is no, it is not reflexive, okay? Because the way you check is for each element of X, you want to see if that element and itself as a two tuple is an element of R. R is an empty set, which means it has no elements. So that means automatically element AA is not in it, element BB is not in it, element CC is also not in it. So it is not reflexive. Okay, so I will basically answer this question is not. Okay, and I'm going to use a subpoint here, okay, because later on you'll see why I do this is not reflexive. Okay, there we go. Do we have any questions about why R as an empty set is not reflexive? Okay, so I have another example here. Okay, this time I define R to have AA, BB, and also CC. And the question is this one reflexive or not? What do you think? Oh, I forgot to close dollar sign, so that's why it looks a little bit funny. Okay, let me close that. There we go. So is it reflexive or not? It is reflexive, okay? Because for every element in X, okay, such as element A, AA is in the set, BB is in the set, CC is also in the set, and therefore it is reflexive. Okay, so it is reflexive in this case. All right, so let's look at yet another example. This time R is just AA and BB. Okay, so like so. And is this reflexive? It is not reflexive because it is missing CC. If it had also CC in it, it would have been reflexive. This is not reflexive. All right, so I'll give you one more example. So this time I'm using the set of AA, AB, BB, and CC. So the question is this particular R reflexive or not? Well, I missed an open paren here. Let me fix that first. There we go. But is it reflexive? And why do you think it is not reflexive? Because, okay, so now you have to be careful with the quantified expression. The quantified expression says for every element in X, we need that element to relate to itself using R. Does it say anything about either, does it say anything about whether an element can or cannot be related to things other than itself? It did not say anything about that. So that means, you can have additional elements, but it does not impact whether it is reflexive or not. So this is still reflexive because this statement here for every E in X, EE has to be in R, does not exclude other elements to be in R. Okay, so this is important, okay, because it is about the interpretation of, the for all thing, and also, what do we do with whatever predicate is quantified. Any questions? I see a few people having an expression, okay, kind of indicating they might have some questions. So is that okay? Yep. Mm-hmm. So in this very specific example, reflexive means AA in R and BB in R and CC in R. But it doesn't say anything about AB or BA or AC or CA or BC or CB. So we only need AA, BB, CC to be in R in order for something to be reflexive. If it has some additional elements, hey, not a problem. Yep, that is a very good question. Okay, so let's look at the other example where X itself is empty. Okay, so I'm gonna do, okay, this is what I'll do. Make this a point and then make all the subpoints indent a little bit more. Okay, so how many lines do we have? 8 lines. So 8, substitute beginning of a line with 2 spaces like that. There we go. Yes, that's the power of VI. And Joplin has key binding, VI consistent key binding, which is good. Even in a class like this, what I just said is extremely geeky. But it's, I think many of you will learn that VI as an editor is actually quite useful, quite important. Okay, so now the question is this reflexive or not? Hmm, that's a very interesting question. Okay, and by the way, this is the only relation that can be defined when X itself is an empty set, because R has to be a subset of the Cartesian product between X and itself. So the Cartesian product of an empty set with itself is an empty set. So that means the empty set is the only possibility as a relation over this particular X because X itself is an empty set. But the question hmm, is this actually reflexive or not? What do you think? It is. Yep. It is in fact reflexive. It is a conjunction that has nothing in it except for the identity of conjunction, which is true. Yep. It has no requirement. So it's that, and that's why I said, it for the most part you don't see it as a function. The only I'll talk about it later, but right now we will simply not look at relations as functions. Yep, because the Cartesian product of an empty set in itself is an empty set, and the only set that can be a subset of an empty set is the empty set itself. Yep. All right, are we are we good so far with reflexive? Okay. All right, so if we're good with reflexive, we'll move on to symmetric. So this quantified expression here is what it takes for a relation R over set X to be called symmetric. So I'll read it out a little bit here. For every E and F in X, and EF can be the same or different, EF as a two-tuple in R, if and only if FE as a two-tuple is in R. That is the quantified expression. If this quantified expression is true, then if and only if this quantified expression is true, then we can say that R is symmetric. Are we good so far? All right. So now we go back to the examples. So this is the reason why I want to kind of do it this way, because I also want to say whether this one is reflexive or not. So X itself has A, B, and C in it. The relation is empty. We know this empty relation is not reflexive in this case, but the question is it symmetric? In other words, no matter what I choose as E and F, do we guarantee the if and only if inside the within the quantifier is always true? Can we guarantee this if and only if is true regardless of how we choose E and F from X? That really is the question. Well, think of it this way. What do you think of this element of and also the other element of? In other words, what is the truthfulness or the value of this element of expression and also this element of as an expression when R is empty? Okay, we know R is empty. So I'm really asking, can an empty set have an element? The answer is no. Okay, very good. Okay, so that means the answer is false. So this element of the left-hand side is guaranteed to be false because nothing can be in an empty set. This element of is also guaranteed to be false because nothing can be in an empty set. So that means both sides of the if and only if are guaranteed to be false at the same time. So what it really is now asking is, what is the value of false if and only if false? How would you answer that question? It is true. And how do we know that is true? It's the truth table. And when did we talk about that truth table? Yep, Boolean operators. That's on day one. That is correct. Very good. Okay. So that means we now know that this is indeed symmetric. What about this one here? Is it symmetric or not? Okay, let me point to the right-hand side here. Is this one reflexive? We got AA, BB, CC in it. Is it reflexive? Yep. Is it symmetric? Yep, it is indeed symmetric. Huh? Why is it symmetric? Because the quantified expression is true. So when you look at this, okay, when you look at this particular expression, okay, so I'm trying, let me see if I can use a double loop to tell you guys what this means, okay? So when we use this notation, okay, so let's say we use the same assumption, X has A, B, and C in it, okay? When we want to evaluate um, for all, oops, for all EF in X, in R, in X, okay, never mind, in X, um, some P of EF, okay? So P is just a predicate, okay, which is an expression that somehow involves E and F, okay? We don't even care how it is used. So what this means is you need to look at 9 cases. So the first embedded case is when E equals to A, okay, and then E equals to B, and then E equals to C. And then there are 3 subcases under this, which is when F equals to A, B, and C. Oops, B, C. And then these 3 are copied over here and also here. So those are the 9 cases that you have to consider is when E equals to A, F equals to A, when E equals to A, F equals to B, when E equals to A, F equals to C, and so on. So now the question is, with the example that we're looking at, what is the result of the expression that is quantified? Okay. In other words, we are now, okay, let me make the window smaller so it fits better because I still want this to be within view. So I have to kind of massage the width a little bit here so everything still fits. There we go. Okay. So now the question is, we know how R is defined. So we know that in this case, R is defined to be just AA and BB. Ah, okay, that's my fault, pressing the wrong key. There we go, DD, and we need a close $sign here. Okay. All right, so only with this subcase here, we are asking AA in R if and only if AA in R. Do you guys prefer me to use the actual mathematical notation, or is this okay? This is okay? All right. So what do you think? Is AA in R true? Is AA in R true? What is true if and only if true? The whole thing is true. Very good. Okay. So we have worked out one case. This whole thing is true. And even though you guys didn't say anything, I still prefer to use the actual mathematical notation just because it doesn't take up as much space on the screen. So that makes it a little bit better. This would be a left, right arrow, I think. There we go. And the other in needs a backslash. There we go. Okay, so we good here. Okay. What about the next one? So the next one is really asking AB is in R if and only if BA is in R. So the question is that true or false? What do you think? AB is in R is false. BA is in R is also false. False if and only if false is true. That's right. Okay. So that is true as well. So you can see how this can be a little bit boring. So does anyone have a specific case that you want me to go over? Because they all kind of be like this, kind of boring. Yep. No, 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 it's not mapping. You are okay, so the expression, oh, okay, I lost that one over here. Okay, so this expression is basically saying choose any element E in X, choose any element of F. For every way to choose E and F in X, I need this if and only if to be true. So the question is it true? So for every way to choose a value for E, that has to be an element of X, and for every way to choose an element F, which is also from X, can I guarantee this if and only if is true? And that's why, in this code here, okay, in this not code, but in this representation, I'm enumerating every possible way to combine the value of E versus the value of F. I would not say it like that. I am evaluating to make sure that this if and only if is true. I need to find the value of the if and only if. No, no, I just look it up. I just look at the left-hand side of this if and only if. I look at this expression, which is AA as a two tuple is in R. I look up R, and RR does have AA in it. So that's how the left-hand side is true for the if and only if. And because the right-hand side in this particular case is exactly the same, we also know the right-hand side is also true. So now we end up with true on the left-hand side, true on the right-hand side, and then the if and only if is the operator. So we look at the truth table, true if and only if true itself is true. Well, yes, we are binding variable E to element A in this case, and we're also binding variable F to variable A in this case. Yes, yes, because that's how the original expression was expressed. Yep. So I'm basically substituting the value of E and substituting the value of F before I evaluate the expression. Yep. What would make it false? Okay, well, let's take a look, okay, because we do have one case where it is already false. So we'll look at all of these. Okay, so we are back to this one here. This one is still symmetric, but this one is not symmetric because AB is in it, but BA is not. Yep. Because in this case, if you bind variable, oh, okay, let me scroll down a little bit. All right, so when this is R, and you bind variable E to be A, and then you bind variable F to be B, then we have one side of the if and only if being true, but then the other side is false. True if and only if false is false. The operator if and only if would evaluate to false in that case. But because the whole thing is using the universal quantifier, so that means if I find at least one case where the expression that is quantified is false, then the whole quantified expression itself is also false. Does that make sense? Okay, all right. All right, so that means I can also give you another example where it is symmetric. Okay, so let's go ahead and do that. Okay, so this time I define R to be AB and BA. Okay, so in this case, it is not reflexive because it's missing all three elements. AA, BB, CC are all missing in this case, but nonetheless, it is still symmetric. So are we doing okay so far with symmetry? Okay. All right. So the next one up is transitive, which is a little bit more hairy because this is the only one that involves like three variables. So when I read the quantified expression here, it's basically saying I have three variables, E, F, and G in this case. And by the way, this F and the G has nothing to do with the functions in the Aleph No module. Okay, this is really just random variable names within the context here. This is really local. Okay, so for variable E, variable F, and variable G, for every possible way to find elements of X to instantiate the values of E, F, and G, I need the whole parenthesized expression to be true. So everything from here to this, I need that to be true. Okay. And the last operator is the implication. In other words, I'm really asking, is the implication true or not for every possible way to bind values to E, F, and G. And the only constraint is every single one of those need to be an element of X. Okay, they can be the same, they can be different, doesn't matter. Okay, all right. So this one is a little bit more difficult to figure out, okay, because you have a triple loop basically. So remember the previous one where I have a loop for E binding to every single value in X, then we have a nested loop for F to bind to every single value in X. Now we have another nested loop, the third level of a nested loop to bind G to every possible value in X. But the structure is the same. It's except that we now have it's a triple loop, but it's nested. We have basically a loop inside a loop inside a loop. We are looking at how many cases. Given that X has elements A, B, and C, how many cases are we evaluating in this universally quantified expression? 27 is correct because 27 is 3 to the power of 3. The first three, the base, refers to the number of elements in X. The other three refers to the number of variables that we are involving in this particular loop. Okay, so let's take a look at all the possible cases here. When R is an empty set, is it transitive? It is transitive. Okay, very good. Okay, you guys are starting to get this. It is transitive. And it is easy to see how it is transitive because what kind of element is is an empty set? There's no element in an empty set. So that means it's an element of, okay, let me use the mouse pointer because I keep pointing to the screen, but there's one person who is not actually in the class. So that means this element of is false. Well, that's all I need to know. Guaranteed, right? This element of is guaranteed to be false, but this element of is inside a conjunction. If one side of the conjunction is false, the whole conjunction is false. And that's all I need to know, because if the left-hand side of implication is false, what happens to the implication itself? It is true. So that means when R is an empty set, it is automatically transitive. Okay, so that's one is easy. All the examples that we have here, oh, there's one that is not transitive. Okay, it's yeah. Okay, so we'll look at each one and ask you whether it's transitive or not. So what about this one here? Let me see whether you guys are seeing the right thing. Yep. So whether this one is transitive, I need to move the screen over a little bit. This gets a little bit on the tricky side, but I can do something like this. I can scroll this one down just a little bit and then move this one over here a little bit. There we go. Okay. So the question is whether this one is transitive or not. AABBCC as a relation, is it transitive? It is. Yep. So this one is transitive. There we go. What about this one here? We just have AABB in it. So the question is this one transitive? It is also transitive. Very good. Okay. And what about this one here? We have AA, AB, BB, and CC in it. The question is that one transitive? Let me try to scroll. There we go. Okay. So the question is this one transitive? Oh, I'm putting on the wrong, this one here. This one first. There we go. AA, AB, BB, CC. Is it transitive? One way to think of it is you have to find a counterexample where the implication is false. In other words, you're trying to find, okay, is there a way for me to bind E, F, and G to elements of X such that the implication is false? If you cannot do that, then it is transitive. The lack of a counterexample means it is transitive. So in this case, it really is transitive. Okay, this is transitive. And I'll tell you this one is not transitive. You go like, but it looks so neat. Everything is so, symmetric and all, how can it not be transitive? What elements is it missing to be transitive? AA and BB. Because if you bind element E to A, F to B, and then G back to A again, then you will find that this expression, this implication, to be false when R is defined like this. Because AB is in the set, BA is in the relation, but AA itself is missing. For the same reason, BA is in R, AB is also in R, but BB is missing in R. So it has two reasons not to be symmetric, transitive. Is that okay? All right. And then the next one is anti-symmetric. Yep. It is transitive. AA, BB, and CC is transitive. Huh? This one? Well, I will answer your question with a super annoying counter question. Why do you think it is not? It seems to be annoying, but it really is the question to ask. Because in order for something not to be transitive, you have to make this implication false. So you have to find a way to bind values to variables E, F, G, such that this implication is false. Now, to make an implication false is difficult because we need the left-hand side of the implication to be true and then the right-hand side of the implication to be false. So now the question is, can you find me a way to assign values to EFG such that the implication itself is false? And if you cannot, then it is transitive. That is correct. Because in the last test case, which is AB and BA, if I bind A to E, if I bind B to F, I bind A again to G, then we have EF in R being true, we have FG in R also being true, but EG, they're both referring to A, AA is in R, is false. So then we have false, true implies false, the implication itself is false. Is that okay? All right. So transitive is tricky, okay, because we have all the usual cases that you understand about being transitive, and then we have also these kind of little trickier cases. Yep. Yes. You have well, okay, nothing should be random, not in this class. So basically, you're looking at something like this, except that you also have, oh, okay, I have no idea where that comes from. So except if you have a triple loop, now you also have to consider what if G equals to A, G equals to B, and G equals to C. So now these three subcases would be for every single other case because you have a triple loop. Yes, there are 27 cases to test in this case. Yep. Yep. Go ahead. Yep. Definitely. Mm-hmm. Yep. That is definitely true. Okay, but that asks, that question prompts yet another question, okay, which is, um, what programming language would you use in order to handle something like this? What feature is in C++, for instance, to support set operations? What features are in Java to support set operations, as opposed to JavaScript and Python? I mean, you guys are either taking or have taken 430 already, so you guys may have a pretty good idea of how set as a data type is supported or not supported in C++. So what is the answer? Is the concept of a set supported in C++? It's sort of. Anything that is a template class is a sort of. It is a is a template class. Okay, set is a template class in C++, which places a very severe limitation of what elements can be in a set. Okay, because they all have to be in the type of the template T itself. Okay, in the angle brackets. So if you ever need to write algorithms involving the use of set as a concept, you can either implement and roll your own, or a scripting language like JavaScript or Python typically have better support of those concepts. Yep. Array of tuples, it depends on what set operations you want to implement. So if you use an array of tuples, then you have to ask, is the ordering of the tuples important? Because in the set, the ordering is not supposed to be important. So now you have to say, if I need to check whether two sets are the same or not, then you have to basically go through loops to check it, because you cannot just do a regular compare. It does get complicated, okay? Even with the implementation of set as a class in JavaScript, I still have to end up using my own class to implement the general sense of a set. Yep. Hmm. Well, we are looking at the implication. So regardless of what is on the left-hand side and the right-hand side, we are looking for the implication. The only time a relation is not transitive is when this implication itself is false. And the truth table that you were looking at says the only time the implication is false is when the left-hand side is true, but the right-hand side is false. So that's your only chance of making the implication itself false, which translates to that's the only chance that you can show that a relation R over X is not transitive. All right. But you guys can start to see, how the notations that we introduced earlier is becoming more and more important because it is important for us to be able to express these properties using mathematical symbols so that there's no ambiguation. I can look at this quantified expression here and generate the correct code in JavaScript in my head because it is that um, precise. Okay, it's precise enough that I can look at the structure of the quantified expression and convert that directly into JavaScript code. All right, so we have one more, which is probably one of the confusing ones. Okay, it is called anti-symmetric. Okay, and people would go look at this and go like, isn't that just not symmetric? No, 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 no. It is not. It is not symmetric. Anti-symmetric is not symmetric. So we'll take a look at the definition here. Okay, so the way it is defined is we have two variables again, E and F. Okay, let me scroll up a little bit here. So for every way to assign values to variable E and F, as long as that value is an element of X, I need to make sure that this implication is true. In other words, ER is in R, EF in R and FE in R implies E and F are the same. Okay, so now we go back to all the examples that we have looked at. Okay, so I think I missed this one here. This is also transitive and also is symmetric. And okay. All right, so we'll go all the way back here. First question, is this one, when R is empty, is it anti-symmetric? In other words, can I guarantee this implication to be true? That's an easy one, by the way. It is, okay, because when R is an empty set, the element of expression is guaranteed to be false. Okay, so we know this one is guaranteed to be false, and it is in a conjunction, which means the conjunction itself is guaranteed to be false. The conjunction itself is the left-hand side of an implication, which means the implication is guaranteed to be true. Yep, so now we just go like, oh, this one is anti-symmetric. Very good. What about this one here? We have elements AA as a tuple, BB as a tuple, and CC as a tuple in the relation. The question is this one anti-symmetric? It is anti-symmetric. Okay, very good. Is anti-symmetric. There we go. What about this one here? AA and BB are the tuples in the relation. So is this one anti-symmetric? All right. So the way we think about this is we ask, can it possibly be false? In other words, can we find EF in R and FE in R and E and F basically are not the same? So the example that we have here is nope, we cannot find the implication to be false because every time we have elements in R, the two elements of the two tuple are the same. So that means E and F are guaranteed to be the same. Whenever the conjunction is true, the equality is also guaranteed to be true. So that means, yep, this one is indeed anti-symmetric. There we go. What about this one here? AA, AB, BB, CC are the elements in the relation. Is this one anti-symmetric? So I'm going to ask that super annoying question. Why do you think it is not? It is true. It is symmetric and it's anti-symmetric. Okay, we only got one to go. Okay, I know you guys are waiting to get out of here. This one is not anti-symmetric because if E equals to A, F equals to B, then this expression, the first part is true, but the second part is false. So we have true implies false, which means the implication itself is false, and as a result, it is not anti-symmetric. All right, so this is all we have time to cover, and I'll see you guys next Monday. Have a nice weekend. I don't have any actual homework assignments right now, okay? But you can go over the examples that we have talked about today, okay? Yep. Um, Hopefully within a week before the break. Yep. Yep. Uh-huh. Ah, because if you put an and here, then this is for symmetry, right? If you put an and here, then the empty set would not be symmetric. And it leads to some other problems too. Yep. Mm-hmm. All right. Uh-huh. Yeah, it's okay.